Is there a difference between 2 meters and 2.00 meters? They may seem like the exact same measurement, but in physics, those extra zeros can completely change what that measurement is telling us. So, in this video, we're going to talk about significant figures, what they are, why they matter, and how they connect directly to measurement and uncertainty. But before we begin, I'd like to ask that if you find the video helpful, please hit the like button, subscribe if you haven't already, and share this with someone who may also find this helpful. I also encourage you to leave a comment with any questions or suggestions you may have. In the last video, we discussed measurement and uncertainty. We learned that no measurement is exact, and we introduced the idea that uncertainty tells us how confident we are in a measurement. But there was one important detail that we briefly mentioned without fully exploring. I stated that most of the time, we don't explicitly write the uncertainty using plus or minus notation. Instead, the uncertainty is often implied by the last digit of the measurement, and that idea is directly connected to significant figures. So, first, why do we even need significant figures? Well, imagine I told you the length of the table was 2 meters. In the previous video, I asked what exactly did you do when measuring the length of the table? You assigned a number and a unit to a physical quantity. But now I want to ask a different question. What exactly does that measurement tell us? At first glance, it may seem perfectly clear, but there's actually an important piece of information missing. How carefully was this measurement made? Do you see that the problem here is that without some indication of precision, a number by itself can be misleading? Remember that we want reliable measurements. Significant figures give us a way to communicate the precision of a measurement. They tell us which digit or digits we trust and which digit is uncertain. So let's take a look again at these two measurements, 2 meters and 2.000 meters. These measurements are indeed different. The first suggests the measurement was only made to the nearest meter, but the second one suggests that the measurement was made to the nearest thousandth of a meter. So even though the numerical values look similar, the level of precision is completely different, and that's pretty much what significant figures are all about. Significant figures are the digits in a measurement that carry meaningful and reliable information about its precision. Now, before moving on, I want to clarify something and be very careful with my wording. It's not necessarily the last digit of a number that is uncertain. It's the last significant digit, the last significant figure of a number that is uncertain. And so that immediately raises a new question. How do we determine which digits are actually significant? We need rules to help us identify significant figures so we can then determine which digit carries the uncertainty. There are 4 rules we need to discuss. Let's begin with the first. Any non-zero digit is significant. That seems simple and straightforward, and it is. The first rule already tells us that 0 is the only digit we have to, in a sense, worry about its significance. Let's quickly go over 2 examples. The first is the number 24. There is a 2 and a 4. Both are non-zero digits, and so the number 24 has 2 significant figures. Next, let's look at the number 3.141. This number is composed of non-zero digits, meaning they're all significant, and so we write that the number 3.141 has 4 significant figures. The second rule is that any zeros between 2 significant figures, or in other words, any zeros between 2 non-zero digits, are themselves considered significant. In this number, the zeros are trapped between non-zero digits, so they're considered significant. This number has 4 significant figures. Now, the last 2 rules can be a bit confusing, so I'll try and explain them in 2 different ways. The third rule is that leading zeros are not significant. Suppose we write something like 0.0042. The zeros in front are only placeholders. They're not telling us anything about precision, so only the 4 and the 2 are significant. The fourth rule is that trailing zeros after a decimal are significant. Consider the number 2.300. These zeros matter. They tell us the measurement was made with greater precision. So we say that this number has 4 sigfigs. Now, I did say these could be a bit confusing, so let's see if the following helps. The first 2 rules seem simple enough. Any number that's not 0 is automatically significant. Any zeros between 2 significant figures are considered significant. So let's go ahead and take a different approach with the last 2 rules. From now on, if you see you're dealing with a decimal, cross out all the zeros that come before the first non-zero digit. They are not significant. However, any zeros after the first non-zero digit are considered significant. For example, if you get something like this number here, cross out all the zeros before the number 4. They are not significant. The 4 and all the numbers after it, including the zeros, are significant. Now, if you're not dealing with a decimal, then any zeros after the last non-zero digit are not significant. So if you were to get something like 42 million, notice this is not a decimal, so you cross out the zeros after the 2, meaning there are only 2 sig figs. Let's go over a few more examples. Consider the following number. Pause the video and try to determine the number of sig figs. Non-zero digits are automatically significant, so we know we have a minimum of 4. Now we have to determine if the zeros are significant. There are 2 zeros between 2 non-zero digits, so according to Rule 2, they are considered significant. But what about the last zero? Rule 3 tells us what to do when dealing with decimals. Remember, when dealing with decimals, any zero after the first non-zero digit is considered significant. The first non-zero digit is the 2. That means the last zero is significant. In fact, all digits in this number are significant figures, so we write 7 sig figs. Consider the following number. Pause the video and try to determine the number of sig figs. Non-zero digits are automatically significant, so we have a minimum of 2. Now we determine if the zeros are significant. Rule 2 tells us that all zeros between 2 non-zero digits are themselves considered significant. Therefore, we conclude that all digits in this number are also significant, and we write 7 sig figs. Consider this number. Pause the video and determine the number of sig figs. Rule 1 tells us that all non-zero digits are automatically significant, so we have a minimum of 2. Next, we determine if the zeros are significant. The third rule tells us about dealing with decimals. It says that when doing so, cross out all zeros that come before the first non-zero digits. That means these zeros are not significant. But what about the 2 zeros between 9 and 4? Rule 2 says that any zeros between 2 non-zero digits are themselves considered significant. So then our answer is 4 sig figs. What about the following number? Pause the video and determine the number of significant figures. Any non-zero digit is considered significant, so that means we have 1 so far. Now we determine if the zeros are significant. Since we're not dealing with a decimal, we take a look at Rule 4. It says that when a number is not a decimal, cross out all zeros that come after the last non-zero digit. They are not significant. Therefore, this number has only 1 significant figure. Let's do one more. Consider this number. Pause the video and determine the number of significant figures. This problem is a bit tricky. The number is actually a decimal, notice the point at the end. I've never seen this as a measurement, but I have been asked a similar question. Since this number is a decimal, then all the zeros that come after the first non-zero digit are significant. Therefore, we have 7 significant figures. Now, here's the most important idea in this entire topic. In a measurement, the last significant digit is usually the uncertain digit. So if I write 2.35, what I'm really saying is I trust the 2, I trust the 3, but the 5 is estimated. And this connects directly back to uncertainty. Instead of explicitly writing 2.35 centimeters plus or minus 0.01 centimeters, we often just write 2.35 centimeters and understand that the uncertainty is implied in the last significant digit. Now, all this raises a couple of important questions that can be easily overlooked. What happens when we perform calculations with measurements? And should our final answer contain more precision than the measurements we started with? No, physics is not just about getting numbers. I mentioned this in the last video. We want reliability. It's about honestly representing what our measurements actually support. So significant figures help prevent us from implying false precision. When multiplying or dividing, the final answer should have the same number of significant figures as the measurement with the fewest significant figures. Now, with that said, there's an important practical detail I need to make known. You should avoid rounding too early during intermediate calculations. In other words, it's usually best to keep the extra digits your calculator gives you while working through the problem. But once you reach the final result, that's when you apply the significant figure rules and round appropriately, because if you round too early, those small rounding errors can accumulate throughout the calculation and actually affect your final answer. Let me give you an example. Consider the following. Pause the video and give it a try. Let's go ahead and ignore the fact that we can input these numbers into a calculator all at once. We start with 3.0 times 2.516. This gives us 7.548. We'll keep all those digits because we're not done with the calculation. We multiply 7.548 times 9.50. Doing so, we get 71.706. Now that we're done with the calculation, we consider significant figures. Which number given in the problem has the least amount of significant figures? That would be the 3.0. It only contains 2, thus our final answer should only have 2. The first 2 sig figs of our result are 7 and 1, But here's the thing. Once we've identified the last significant digit, we must look to one more number to the right. This is to round. Given that the next number is greater than 5, the 1 is rounded up to 2. So our final result is 72. There are additional rules for addition and subtraction involving decimals, but for now I just wanted to focus on the rules you'll most likely encounter in your calculations. Now that we've gone over significant figures, when multiplying and dividing for that matter, I want to re-emphasize that one of the biggest mistakes students make is treating calculators as if they determine precision. But calculators don't understand uncertainty. They'll happily give you 12 decimal places even if your measurements include a number with like only 2 sig figs. If you're finding it difficult to determine how many sig figs to use in your answer, a safe guess is usually 2 or 3. Just don't go putting all numbers displayed in your calculator as your final answer. So to summarize, significant figures are more than just rules about zeros. They're a way of communicating the precision of a measurement. They tell us which digits we trust and which digit is uncertain, and they ultimately help us represent measurements honestly. Anyway, that is it for this lecture video. I leave the following problems for you to try. As always, I'll post the answers at the end of the next video. If you found the content helpful, I'd again like to ask that you subscribe, hit the like button, or leave a comment. Here are the answers to the last video's practice problems. I'll see you in the next one.